All right, so picking up on problem 33, we have that a regional transportation authority is interested in estimating the mean number of minutes working adults in the region spend commuting to work on a typical day. So a random sample of working adults will be selected from each of the three strata: urban, suburban, and rural. Selected individuals will be asked the number of minutes they spend commuting to work on a typical day. Why is stratification used in this situation? Okay, so first reviewing what it means to stratify. That's when you're basically breaking up groups, or when you're breaking up a large group into subgroups where each subgroup is similar. So like maybe like if you're going to take a sample of high school students, maybe your large group is like all the high school students from 9th to 12th grade. But if you want to study like average height or something, you probably want to break them into strata according to like their age or like grade. So like one strata would be like 9th graders, another would be 10th, another would be 11th, and another would be 12th. Now what this is going to do is it's going to help reduce the variability among your estimates when you're, trying to, estimate something. So it's not going to remove bias. That's what random sampling does. We random sample in order to reduce or remove bias. And so we want to look at variability, and it's going to be E because we're looking for the proportion. We're looking for the total. We're looking for all these adults and their average mean time to work. We're not looking for like the mean time among each subgroup. So our answer will be E. (34). We have a randomized block design will be used in an experiment to compare two lotions that protect people from getting sunburned. Which of the following should guide the formation of the blocks? Okay, so again, when you're doing an experiment, it's pretty similar to doing stratified sampling. You want to basically make blocks where you think there's a variable that could affect the results systematically. So maybe if you're trying to measure like the average time a high school kid takes to run a mile, you're probably not going to want to mix in like the high school like track team with just everybody else, especially if you have a small group, because like the track athletes are going to be most likely in better shape than the average, high school kid. So your blocks would maybe be like the track team, and then kids maybe not on the track team, that sort of thing. In this case, since we're talking about lotion that protects people from getting sunburned, we're going to want to, account for the fact that some people, get sunburned more easily. So let's see which of these would work. So participants should be, yeah, so it would be D. Participants within each block should be as similar as possible to respect how easily they get sunburned. So maybe like one group would be people that get sunburned easily, another group would be medium, another group would be people that rarely get sunburned. (35). A group of students wanted to investigate the claim that the average number of text messages sent yesterday by students in their school was greater than 100. They asked each student in a random sample of 50 students how many text messages he or she sent yesterday. An appropriate t-test was conducted and resulted in a p-value of 0.0853. Assuming the conditions for the t-test were met, which of the following is an appropriate conclusion? Okay, so reviewing how significance value works. When you run a significance test, you have an alpha level, like usually it's set at 0.05, sometimes it's 0.101, and then sometimes even 10%. Now, when the p-value is less than your alpha level, then you have reasonable evidence to reject the null hypothesis. When the p-value is greater, you don't really have evidence or strong enough evidence to reject your null hypothesis. So the p-value is lower than the 0.1, but it's not lower than the 0.05. So at 0.1, we would reject the null hypothesis and say that, yeah, there's significant evidence to say that the mean number of texts sent is more than 100. But let's look at what we have here. So at 0.1 is less than 100. No, we want the other way. Cannot be concluded. So yes, these are kind of backwards. They're doing it backwards. If this said if this said more than 100, that would be okay. And if this said it can be concluded. Now, at the 0.05 level, we're gonna fail to reject. So we can't say it can be concluded. So then it cannot be concluded that the mean number of text messages sent yesterday by students at the school. Yeah, so our answer would be E, because this is essentially saying that we're gonna fail to reject the null hypothesis. We can't really say that our evidence is strong enough to claim that the mean number of text messages is more than 100. Our two college roommates have each committed to donating to charity each week for the next year. The roommates' weekly income are independent of each other. Suppose the amount donated in a week by one roommate is approximately normal with mean $30 and standard deviation $10. The amount donated in a week by the other roommate is approximately normal with mean $60 and standard deviation $20. Which of the following is closest to the expected number of weeks in a 52-week year that their combined donation will exceed $120? Okay, so this is going to be basically calculating the probability of a random variable. So let's have one roommate be the random variable x. So they have a mean of $30 with a standard deviation of 10. Let's have the other roommate be by. So they have, so they have, well, they have let me just write this up. They have a mean of $60 and a standard deviation of 20. But now we're going to look at a third variable, or let's call it t, where t is the sum of their donations. So x plus y. So then we're going to have the mean of t be equal to the mean of x plus the mean of y, which is going to be 90. And the standard deviation of t, for this, we have to calculate the variance of t. So we're going to have the standard deviation be equal to the square root of the variance of t. Now the variance of t is equal to the variance of x plus the variance of y. This is probably the one thing you have to really remember when you're talking about random variables, is that you can't simply add the standard deviations, but you can add the variances and then take the square root of the sum of the variances. So then taking the variances, we're going to get that the variance of t is going to be 10 squared plus 20 squared, or 100 plus 400, or 500. And so the variance or standard deviation of t will be the square root of 500. Decimal approximating, we get about 22.36. Now we're going to look at a distribution with the mean of 90 and a standard deviation of 22.36. And remember, we're trying to find the probability that it's greater than 120. We're trying to find this area to the right, so to speak. So for this, we can use technology. We can go to Stat, Calc. No, not Stat Calc. We're going to go to distribution. So second vars, normal CDF. The lower bound will be 120. Upper bound, make it a very large, like a billion or something. Followed by then the mean, which is 90. Then the standard deviation. And that should give us about a probability, about 8.9%. About 9% almost. No, this is basically saying about 9% of the time, or 9% of the weeks. So we take this number and multiply it by 52, and that'll tell us about how many weeks. So about 4.67 weeks. So this times 52, 4.67. So the closest answer will be 5 weeks. And so the answer will be D. Number 37, a university will add fruit juice vending machines to its classroom buildings if the student body president is convinced that more than 20% of the students will use them. A random sample of N students will be selected and asked whether or not they would use the vending machines. A large sample test for proportions at the significance level of alpha equals 0.05 will be performed. The null hypothesis that the proportion of all students who would use the vending machines is 20%. We tested against an alternative that more than 20% of all students would use them. For which of the following situations would the power of the test be highest? Okay, so power is a pretty complex topic. It's not covered in depth, and it's not tested in depth on the AP exam. Um, I can imagine that if you go into more higher level statistics, it will be. But you really just want to understand that power is good. The higher the power, the better the sampling method, the better the test. So you want higher power. Now just think intuitively, what would make sense like in real life if you're running a statistics test? And that would be, the bigger the sample, the better, because you have more information. So always the bigger sample increases the power of a test. And the farther the statistic is from the null hypothesis, that's basically going to be more stronger evidence, because it's like if you're trying to estimate, like let's say you're trying to for me, I always think basketball. If you're trying to see what your true free throw percentage is, if you were to shoot, it's better to shoot 100 baskets than 50 baskets, and which is better than 10 baskets. The more shots, the better. Also, if you want to say, oh, my shooting percentage is 50%, and in your sample you get 70%, then it's pretty good. That's a lot stronger evidence than if you were to get 55% or 51%. The farther your statistic is from your estimate or from your null hypothesis, the better. So we got samples of 750, 1,000. So we can see 50% is the farthest value away from 20, and 1,000 is the largest sample. So this is going to be, I'm going to say right there, E. E is going to be our answer here. All right, 38. Each of the faces of a fair six-sided number cube, or just a dice, is numbered with one of the numbers 1 through 6, with a different number appearing on each face. Two such number cubes will be tossed, and the sum of the numbers appearing on the faces that land up will be recorded. What is the probability that the sum will be 4, given that the sum is less than or equal to 6? Okay, so let's just draw a diagram. It might take a little time, but it'll be good for you guys to see this, especially if you're not strong in your probability. But what we have here is the diagram where we have die 1. This will be like the number you get on die 1. And over here will be the number you get on die 2. And the numbers on the inside, let's just use red, will be the sum of the numbers on each die. So 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4, and so forth. So these are the numbers that the corresponding dies will add up to. And there's going to be 36 total, as you can see. Oops. No, there's 36 possibilities, and it's asking what's the probability that the sum will be 4. There's 3 ways to get 4, given that the sum is less than or equal to 6. So if it's less than or equal to 6, then we're only going to include the ones I'm going to shade right here. We're only going to include the ones that are 6 or less. So there's going to be 15. 15 of the numbers are 6 or less, and 3 of those 15 are 4. So the probability would be 3 out of 15. And they didn't simplify, so the answer will be C. All right, 39. We got to study, compare the language skills and mental development of 2 groups of 24-month-old children. One group consisted of children identified as talkative, and the other consisted of children identified as quiet. The scores for the 2 groups on the test that measured language skills are shown in the table below. Okay, so assuming that it is reasonable to regard the groups as simple random samples, and that the other conditions for inference are met, what statistical test should be used to determine if there is a significant difference in the average test score of talkative and quiet children at the age of 24 months? Okay, so I guess they're just trying to make sure you know the main differences between the tests, because this one shouldn't be too hard. It's not going to be chi-square tests. It's because chi-square tests you're trying to fit. You're basically going to be given like a set of values that you want to see if your data will fit it. You're going to be told like how well does it fit these scores when you're or usually percentages or proportions, but it's definitely not chi-square. Now it really comes down to t-tests, because you're basically testing 2 means, and the key here is to know whether it's a matched pairs or 2 sample, and we're given 2 groups, or a group where we're talking about the talkative kids and the other group where they're quiet kids. So you're not going to have a matched pairs t-test, because when you talk about matched pairs, they're supposed to be similar. That's really as simple as I can put it. Like it's pretty much, and it's like explicitly told to you that they're not similar, that one is talkative and other is quiet. So it's going to be a 2 sample t-test for means. And the last one here. An experiment will be conducted to test the effectiveness of a weight loss supplement. Volunteers will be randomly assigned to take either the supplement or a placebo for 90 days, with 12 volunteers in each group. The subjects will not know which treatment they receive. At the end of the experiment, researchers plan to calculate the mean weight loss for each of the 2 groups and to construct a 2-sampled t-confidence interval for the difference of the 2 treatment means. Which of the following assumptions is necessary for the confidence interval to be valid? Okay, so the issue here is that we have a small sample size. Since we're trying to study means, this falls into the central limit theorem. You know, so, you have the criteria central. I didn't know what word I wanted to use, but we have to look at what the central limit theorem says, and that's when your sample size is less than 30. Usually it's 30. Some books have it 25, but I think in this course and on the exam, they're always going to say 30. It's going to be like your boundary value. If your sample size is not at least 30, then you have to check and inspect the sample shapes. And you want them to be roughly normal, or at least for them not to have any strict like skewness. You don't want them to show that they're not obviously normal. So it's not going to be this 10%. Yeah, we're going to want C will be our answer. That's the one it talks about. And this is going to be like chi-squares. These are like chi-squares. This is supposed to be the other way around. This is supposed to be greater than, or I'm sorry, less than 10%. You know what? That's for the standard deviation value. Anyways, so the answer will be C. All right, so there's the rest of the practice section of the multiple choice section. So next I'm going to go over the free response. But let me know which problems you want me to focus on, or if there's any other concepts you want me to go over. And if you haven't yet, make sure you subscribe and give me any feedback in case there's any problems I might have explained a little confusingly. All right, thanks guys, and I'll see you guys in the next video.